So let's go ahead and start our discussion of noise. In particular, thermal noise, because this is the one that usually gets us as satellite engineers. Okay, so here's the basic process that we're interested in. First of all, we just said where noise comes from. Noise is this constant barrage on any radiating device of background radiation. It's hopelessly stochastic. In fact, that's why it's a corrupting influence on data signals, right? It contains information in the sense that it's varied and interesting and unpredictable, but as far as we can tell, there's nothing useful about it. And so it winds up competing with the detection of a desired signal. Now, the best way to talk about noise is to characterize the statistics. And, not surprisingly, noise follows statistics that are strikingly like the textbooks that you've all discussed probability and statistics with. What's the most common probability density function? What is everything at the end of the day? What do we always approximate it as academics? Gaussians, right? Everything is a Gaussians. I'm sure when I get test 1 scores from this class, it's going to be a Gaussian of some sort. If I measured the heights of people that walked into this room to sit down in this lecture, it's going to be approximately Gaussian. Some sort of mean and standard deviation and a bell curve around it. And noise is really no different. Why is the Gaussian so darn common when we study statistics? Why? Because any statistic that is based on the sum of lots of random events basically follows the law of large numbers, right? And that statistic always tends towards a Gaussian. And so if I have an antenna and I have thousands of photons of all the different frequencies raining down on that antennas, at any given instant in time, I'm going to get a bunch of either constructive or destructive interference as those different frequency photons add up or cancel. And they're going to follow the law of large numbers, too. They're going to be zero mean, because if I add up a bunch of randomly phased things, I always get zero mean. And if I look at the absolute voltage, it's going to follow a Gaussian. So it'll have a standard deviation that's going to be roughly proportional to the RMS voltage, or the square root of the average power of the noise process. Now, there's a very nice formula in radiation theory that allows us to calculate what that average power is. So, first of all, if I look at a noise process, let me sketch this out. I'm just going to see garbage at my antenna. If there's no real information signal present, I'm going to see something that if I took a histogram in voltage, so say this is voltage, it's going to have a standard deviation noise, zero mean, and it will have a Gaussian distribution. And we would call this the first order statistic. There are lots of things that are Gaussian. I can have a slow, not so random variable signal that could have the same type of Gaussian statistics. It doesn't say anything about the evolution of the signal over time yet. We haven't made that part of the analysis yet. However, it does say what the amplitude distribution is going to be. And so, in fact, if you look at an antenna, at the terminals of an antenna, any antenna, normally we model it as some sort of sinusoidal voltage, and of course there's an antenna impedance. Yes. Say it's resonating. We've gotten it down to purely real. And that's the model that we use for an antenna. However, these other signals that are coming in, This is going to be a Gaussian distribution that is zero mean and has standard deviation sigma sub n. Okay. Now, here's the other thing. I just said that these photons are coming in at virtually all frequencies. If you look at it over a narrow band, the frequency excitation is roughly the same. And so that type of noise we call white, which means if I put this on the network analyzer and I look at the signal real time in the frequency domain, or the spectrum analyzer, my device of choice here, what I would see, if I looked at noise power as a function of frequency, is a roughly flat line over the band of interest. We usually denote that power level as n naught. This is in watts per hertz, which the astute student will realize is actually joules. But it makes more sense to think of it in terms of watts per hertz on this screen of a spectrum analyzer. How do we know it's white? What does that mean in the time domain? When a process is white, that means that it is uncorrelated. So we know, for example, that if you studied stochastic signals, you can talk about a random process's power spectral density. And another way to characterize the random process evolving in time is to use an autocorrelation function, studying how does one part of the process relate to another part of the process in time. The autocorrelation basically tells you how those different points in the process relate as you change the observation window, move the points farther apart in time. And that gives you an autocorrelation function. Now, who here is a 7th level DSP master and has taken some of our stochastics course and signal processing courses? What's the relationship between the autocorrelation and the power spectral density? I think I heard it. What was it?
Fourier pairs.
Fourier pairs. That's right. Exactly right. Exactly right. The autocorrelation is the Fourier transform pair of the power spectral density. What does that mean? Well, I've got a perfectly flat white noise process. My power spectral density is a constant. What's the Fourier pair of a constant? A delta function, right? That's a constant is the widest possible function. So in the alternate domain, it's always a delta function where the power is collapsed to a single point. Well, what does that mean? That means that really, if I go take a point of observation in the time domain of this process, and I move just a little bit to the left or to the right, no matter how little I move to the left or to the right, that next measurement in time tells me nothing about the adjacent point that I first started to observe. Only the point tells me about the point. That's what a delta function autocorrelation means. And there's a very elegant proof in stochastic processing theorem, in a theory. It's called the Wiener-Canchin theorem. And it basically says that the Fourier transform of the autocorrelation is the power spectral density. So there's always a frequency domain way of stating that. The way of stating that this thing, one point doesn't tell you anything about any of the adjacent points anywhere else on the time domain, that's basically saying, oh, this has a white power spectral density. I'm exciting all frequencies uniformly. Remarkably powerful theorem in communications and signal processing, the Wiener-Canchin theorem. It will not be the last time we invoke it in this class. But it basically tells us, just through this physical reasoning of the fact that I have all these photons raining down on an antenna at all frequencies, producing Gaussian, uncorrelated time domain voltages, that means I'm going to have a white frequency response. Now, in truth, there's no such thing as a pure white process, right? If you look over very, very large radio spectra, this curve will undulate slightly. And particularly at higher frequencies, it will eventually fall off and taper. Why? Because you can't have a constant watts per hertz that goes on forever. Otherwise, I'd integrate it from 0 to infinity to get the total energy out of the power spectral density, and I would have an infinite number of watts being I would solve the world's energy crisis just by holding up an antenna and looking at the black body radiation. Not possible. Not possible. At some frequencies, it eventually fizzles out completely. But this is the basic model. And what's more, I can even calculate what N naught should be based on black body radiation theory. So you figure out N naught by and actually, classically, we divide by 2 here when we do the power spectral density to get the math to work out with thermodynamics here. So my power spectral density of noise is N naught over 2. N naught is equal to Boltzmann's constant, which you've probably seen in thermodynamics or some physical chemistry, perhaps. 1.39 times 10 to the negative 23 joules per Kelvin. This is a natural constant. And multiplied by the physical temperature in Kelvin. The physical temperature is the average background temperature that an antenna sees in its field of operation. And that's actually kind of tricky. It's usually given in a problem or a spec sheet. People have measured antennas in different scenarios. It's not the easiest thing to calculate, but we have a lot of really useful thumbs that get pretty close to what the physical temperature of an antenna sees. So for example, if I just took a little omnidirectional antenna, a little dipole of some sort, and just held it out here in this room, what would the physical temperature be? Well, room temperature is probably about 270 Kelvin. I'd probably just use 300 Kelvin in my calculations because it's a nice round number. I guess, no, 273 is 0 Celsius. So 300 is good estimate for room temperature. And you find a lot of RF measurements with respect to noise are made at that reference temperature, 300. That's a good reference. That's not true if you had a really directional dish and you pointed it up to the black sky at night. In that case, your dish now has a very tightly focused beam that's pointed up into the heavens, and we know that the background temperature of black space is much, much lower than 300 Kelvin. Of course, you have to go through Earth atmosphere, and there's some warm air in that column that's going to add some noise. If you move that dish into outer space, then you just see like the 3 Kelvin background blackness of space, whatever was left over in the Big Bang in terms of background thermal energy. You can actually measure that if you get out into space very cleanly. And so here, that temperature, you're talking about a single-digit Kelvin in that scenario. If you happen to be pointed into the sky and the sun passes into the main beam of your antenna, all bets are off, and you've got tens of thousands of Kelvin, and your noise floor just spikes. This thing just raises up a few 20 or 30 dB, often to the point where you'd lose a signal. But that's a rare occurrence. The sun won't be in your beam for more than a few minutes. You just have to be a very unlucky satellite Earth station operator if that happens. Okay, so we now know what this level is, which means we can actually calculate the power in a signal. So keep in mind that this floor, this noise floor, occurs at all frequencies. But all of our signals are band limited, which means they're going to have a bandwidth B, and most of their energy is going to be concentrated in that bandwidth. So that I can effectively drop this through a bandpass filter, and most of the noise that comes out of the terminals of the antenna here, I can filter out. But the stuff, of course, that's in band, I can't filter this stuff out without damaging the information in my signal. And so, generally speaking, B is the irreducible amount that you can filter noise out and still have a viable detected signal. Some people call B the noise equivalent bandwidth. It's not necessarily even the bandwidth of your signal. It's kind of how do all the filters operate in your signal and how much noise do they leave over, equivalent to a perfect brick wall bandpass filter at the end. We can use the bandwidth of the RF signal in this class to basically approximate the noise equivalent bandwidth without doing the fancy analysis to calculate noise equivalent bandwidth. It gives you almost the same value, but just recognize that there isn't a magic perfect filter to drop these signals there that are exactly B. They have some taper to them as well. And this idea of a fixed square filter B is idealized, like much of everything that an academician puts on a board, right? You know that caveat already. You've been in school too long already. Okay, so if this is the watts per hertz, all we need to do to calculate noise power is to multiply K, T physical, times bandwidth. And that gives me a result that has units of watts. Remember, this is joules per hertz, watts per hertz, which is joules. And I multiply it by bandwidth, that gives me watts. Now, the reason why there's an n naught over 2 here is because, remember, in the frequency domain, I've got the main positive frequency spectrum, and I've got its conjugate mirror image over here in the Fourier transform. Both of those allow n naught over 2 plus n naught over 2 to drop through the system at bandwidth B. Okay. And, of course, if you're at all interested in modeling this from a circuit point of view, the noise here, the standard deviation of the voltage signal in this case, would be, let me see if I can remember this, 2 K, Boltzmann's constant, 5 bandwidth times RA. Why? Because this, if you were to give it a matched load, an RL that was equal to RA, and you took away the voltage, the signal source, if you just had thermal noise coming in through the system, the power that you would absorb at the load is this. You can actually work it out if you want. Do your voltage divider, take the average value of a Gaussian random voltage after it's divided across that RL, and you'll find that this is the power that you would absorb. Under match, you actually absorb less of it if you're mismatched, but of course you absorb less signal too, so that doesn't help you by thinking you're going to mismatch the antenna to get rid of noise power. And also, the other thing to keep in mind too, and this gets to the heart of our next section of the discussion, is that this sucker isn't at absolute zero either. It's going to have, we don't usually think about it because it's a very small component of the signal, but there is also a random value of noise being generated by that resistor, R sub L. It has its own system temperature, its own device temperature, and because it is not at absolute zero, it will impart electrical energy this way. You say, well, wait, resistors generate energy? Is that possible? Did I just solve the energy crisis again? No. Because, and you can work this out, the resistor will also have, let me put it on this pane, let's call it sigma sub R. It will have a voltage that is 2 K T sub R BRL. And if you work through the mathematics, you can show that that antenna and the resistor are exchanging no net energy to one another if The system is in thermal equilibrium, just like you would expect in thermodynamics, right? This way of modeling circuits and devices, this is the Johnson model. I think I've heard it called the Johnson-Nyquist model as well for noise on a device. Any device, a diode, a capacitor, etc., they will all have this kind of noise or something related to it associated with it, unless the device is at absolute zero. So that raises a question. I've got an antenna. The background radiation is coming into the antenna along with the signal. And I'm going to run it through devices. I'm going to run it through filters. I'm going to run it through active devices like amplifiers. And keep in mind, what is an amplifier? An amplifier is, at least from a thermal perspective, a very hot device because I have to bias it to get active gain. I run DC current through it to bias it, and I pass the signal through it. So that device is going to add more noise on top of what's already there. In fact, in some cases, it's going to be a lot more noise than what I would normally get just with my physical temperature coming in. And so I'm going to teach you the way that RF engineers and satellite engineers track noise in a sensitive receiver system. This is going to be how they think of it and how they model it. So what we'll do noise in an RF system. Okay. We've got an antenna. I've got a received power. Let's call it PR0. The zero to denote that this is ground zero, the very start of the signal. And I also have PN0. This was K T5B, and this is whatever my link budget would predict it to be. Again, the noise at the very terminals of the antenna. What's the first thing an RF engineer does to a signal in this scenario? Well, besides simply maybe a little bit of filtering, the real rubber hits the road in terms of noise analysis at the LNA, the low noise amplifier. This triangle. So then the question is, what happens to the received power in this scenario and what happens to the noise power? The relative change between the two will determine the signal-to-noise ratio at the output of this device. I can already calculate it for the input. What is it going to be at the output? Okay, so I'm going to get signal gain here. So this should be gain RF times PRO. Now, the noise that will pass right through this amplifier. So my noise consists of actually two parts. PNO, which will be multiplied by the gain at RF, plus whatever noise is added by the devices in the low noise amplifier. Call this P sub N1 times that gain. And so this is how engineers like to talk about noise. This is how they model it. Whatever the device is here, it has a certain gain factor. We call it gain RF in this scenario. And it will have some internal noise that it adds into the signal. And we typically track it before it hits the gain. So when you see the noise temperature of a device recorded on a spec sheet, they'll give you a noise temperature. And that will basically be K, let's call it TRF, times whatever the bandwidth of your chain is that you're going to allow through the system. These signals that gets added to these signals, and then they experience gain. I guess in a alternate universe, somebody could have decided to put this at the output and just bookkeep that way, but you'd have ridiculously high noise temperatures in that regard, and your spec sheet would look kind of nonsensical. So as a marketing gimmick to make the spec sheets look, at least that's what I suspect, I don't know, to make them look more realistic, we put the modeling on this side. In a way, the noise temperature is kind of convoluted with the gain, right? It's always just an effective noise temperature that you're coming out with. But regardless of how you bookkeep it, there's going to be this additive white Gaussian noise, AWGN, that's added to whatever's existing there, which already has additive white Gaussian noise. And out on the other side, you're going to get increased noise. So the SNR at point 0 was PR0 over PN0. The SNR after device number 1 is when I divide through, the GRFs cancel, and now it's PR0, PN0 plus PN1. So you see this clearly less than that. You've degraded the signal to noise ratio. This is why you use an LNA at your first stage of amplification instead of simply an A. A lot of engineering, a lot more engineering goes into the LNA than it does any successive amplifier in your receive chain because it's the most critical. You usually try even to sacrifice some of the gain. You don't necessarily want to get 20, 30, 50 dB of gain or something ridiculous at the LNA. You just want to get a little bit of gain, 10, 15 dB, with as little noise as possible. And there's some trade-offs with dynamic range, gain, and ultimately how much noise you add to a signal. So this is critical. You'll spend more money on your LNA than any other component except maybe the transmit amplifier, the power amplifier at the end of a chain. Very critical what's going on. And I'll show you, it becomes even more obviously critical when we talk about whatever happens at the next stage. Right? So there's going to be another device here. So let's say I've got multiple devices. Device 1, which has a noise device temperature of T sub 1 and a gain of G1. And let's say I have device 2, and these are generic devices. They could be amplifiers, they could be active mixers, they could be even passive things that could induce a loss. Whatever it is, then the gain is less than 1. I can use the same strategy to model things. If that's the case, then my total signal power, PR2, is going to be PR0 times G1 times G2. My noise at 2 is going to be PN0 times G1 times G2 plus PN1 times G1 times G2 plus PN2, but this time it's only going to be multiplied by G2. Only multiplied by G2. And so, one thing that we like to do in noise analysis is to come up with this concept. Remember, N naught here is, this is K T phi times B. And 1 here is K T1 times B. This is K T2, temperature, device temperature noise in Kelvin of the second device, and so forth and so on. You see, there's a lot of common terms here. We've got a lot of the gain terms are in common. The Boltzmann's constant is in common. The bandwidth is in common throughout all these terms. So when we talk about noise, we like to factor things out. So we have K, B, and all of the gain terms. What's left over when we do that? Well, this term gets multiplied by all the gain terms. So all that's left there is a T phi when you factor all the gain terms out. Same with the second one. The second device, T1, has a noise temperature of T1, and it gets multiplied by all the gains because it appears first in the receive chain. The second one, when you do this factorization, the second device temperature gets divided by the gain of the first temperature, of the first gain. And then then all the other gains factor out. And likewise, the third, if there was a third device, it gets divided by gain 1 and gain 2, etc. All of this together has a special name. This is called, I'll raise up a little higher for you to see, T sub sys, the system temperature. The system temperature. The system temperature gives you an effective number in Kelvin that allows you to track additive white Gaussian noise all the way to the end of the line in the receiver. Now, what do you notice about the system temperature? If you've got a low noise amplifier at the front, the first stage is going to give you some gain, and it gets divided into everything else that comes after this. And this one, hopefully, is not very big. And so this is why the first stage is so critical in RF. You need to add as little noise as possible, and you need enough gain to wipe out any of your noisy devices later on in the chain. In fact, a good, well-designed receiver you can almost always approximate as the the system temperature is roughly the physical temperature plus T1, and maybe a couple fractions of a Kelvin thereafter, if you've done a good job as an RF engineer. But this shows you why that first stage is so critical. This is why for really sensitive receiver applications, for example, like radio astronomy receivers, they use things like liquid nitrogen cooled units as their front-end amplifiers. You pour it into this vat, it's super cooled, and they can basically get the device temperatures down really low so that not that much thermal noise is being added in it on top of what they're observing from the stars. A lot of engineering goes into that RF front end. We don't normally have the luxury of that in a conventional Earth station, certainly not in a handset. In fact, we don't really care too much about thermal noise in a handset, a cellular handset, when we do earthbound communications. Why would that be? Why can we get away with cheap front ends? Because handsets are not noise limited. They're interference limited. Your cellular carrier, unless it is the worst carrier on Earth. No Verizon jokes. No, I'm just kidding. Perfectly fine carrier. That they're reusing their frequency because they had to pay a lot of money for it. Right? And so there's going to be a lot of people using the same frequency bands that if they've done their planning right, they're far enough away that they're only contributing moderate interference, but it's usually more than the noise floor. But in satellite communications, it's usually thermal noise that's really causing us problems in our signal detection. It can be interference as well. So any questions about this analysis before we continue on in noise? I've got a couple of example spec sheets that I'll show you that have some noise figures on it. I want to make one point about noise before I show you that. And this is something that's almost unique to satellite engineers. you now have enough to calculate the SNR of a system. All right, we can use the Frizz free space equation, which says if I know what my transmit power is, and my receiver antenna gain, and my transmit antenna gain, if I know the wavelength and the separation distance, that gives me my signal power. Now I've got to divide it by noise power, which is K T-sys times the bandwidth. Okay, so if I'm an Earth station and I'm doing communications, I only have control at my receiver of two of those variables. Two of those variables. I probably don't have any control over how far the satellite is away from me, so I can't do anything about R. I can't do anything about the transmit antenna gain. I didn't pick the antenna. I'm stuck with whatever the satellite's transmitting with. The frequency is part of the protocol as well as probably the bandwidth, so I can't change those. I'd be really impressed if you could change Boltzmann's constant. You probably deserve to be worshipped at that point. And the transmit power, likewise, is that's fixed. You really only have a control over the receive gain and the system temperature. Your receive antenna gain and the system temperature. In fact, the ratio G sub R over T sys is a really good metric for how well and how sensitive your receiver is. And so this is why Earth station satellite engineers will often talk about their G over T. So what's your G over T? What they're really saying is what is your linear antenna gain over your noise system temperature in Kelvin? Because that's an awesome metric of how sensitive to the receiver is. What do you think the G over T is of a cell phone? Well, we said that G is usually about 1 if you're lucky. And the front end is probably like 1,000 Kelvin system noise temperature, at least. So you have a G over T of, let's say, 0.001 for the cell phone. For some of these more sensitive Earth station receivers, especially those radio astronomy receivers, you're talking about noise temperature down at maybe 100 Kelvin. In a big dish that's giving 60 or 70 dBi, that's not even in the linear scale. So you might have like 10 to the 5th G over T for a really sensitive Earth station. You see, we just went 8 orders of magnitude in sensitivity between the little handset that you buy at the store and the really big Earth station that's doing space communications. So G over T is, you'll see that again if you read some texts and papers in satellite communications. Okay. One more thing before I put up some examples on the light here. There's an alternate way. Sometimes people give you on a spec sheet device temperature, and sometimes they give you noise figure. Noise figure is just an alternate way to report device temperature. The way that noise figure is calculated noise figure is defined as the change in, let's see, SNR of your input over SNR of your output. So I've got a signal with an SNR in. It goes into a device that has gains or losses, and it comes out with an SNR on the output. And of course, the SNR should be larger on the input than it is on the output. So this should be a number that is greater than 1 for most realistic devices. Okay. Now, in this model, this is a very nice way of thinking about signal-to-noise ratio, because the figure noise figure, which I've defined in the linear scale but is often reported in dB, noise figure is nice because it tells you how your SNR is going to change. So it kind of removes you from having to track things like Boltzmann's constant and device temperature and those lower-level physical phenomena. However, in doing so, they've presumed that, in a way, you've got a signal-to-noise characterized already, which means you know what your device, you have a reference temperature, effectively, for what noise is going in. If you change the reference temperature, then the noise figure changes. So, if you want to backsolve a device temperature from a noise figure spec and do everything manually like we did over there, you get your reference temperature, which, unless specified elsewhere, is 290 Kelvin. And then you take your linear noise figure and you subtract 1. Okay, so let's look at an example of an amplifier spec. These are just ones I ripped off the internet years ago. I'll go ahead and go to the document projector here. I have to turn the power on first. Let's see, did I orient this thing properly now? Yep. And light is on. Oh, perfect. Here it is. I just went to the Mini Circuits homepage and grabbed a couple of amplifier specs here. Here's a nice amplifier, 50 ohms, of course. Very broadband, 0.5 to 5.9 gigahertz. And let's see, this is the new, it was maybe new 10 years ago, ZX60M series. Amplifier specs don't change. Nothing's changed about it. So then let's take a look here. Electrical specifications. Of course, there's multiple models. And let's see, where's the noise figure? Does it say? Let's see, there it is. Noise figure. 5.4, it's being reported to in dB. So they just took the linear definition that I put on the board over there, and they took 10 log 10 of it, because noise figure is always in power, so you take 10 log 10. So 5 dB, that means that the noise figure is probably close to 3, almost 4. And if the reference temperature is 290 Kelvin, that would imply that I had a device temperature of, I don't know, maybe 800 or 900 Kelvin for this particular device. Then I look over and I see, oh, yes, it's $59, $59.95. Let's see, and what's the typical gain? So this is going to give you a gain of about, looks like 12 dB across this useful band, which is fairly broadband. Okay, so let's compare that with another amplifier spec. Ooh, this one is a low noise amplifier. Let's see if I can. Oop. Let's see. Okay, good. So this one, not nearly as broadband, 650 to 1200 megahertz. It's hard to make a broadband low noise amplifier. So they've squinted up the bandwidth. And let's see, what's the gain here? The typical gain is about, this one's pretty good. It's about 25 dB, but very narrow band compared to the other one anyway. And the noise figure for this guy has got a whole column, and it's typically 2 in dB. Ooh, that's really good. A noise figure of 2 is really good. It might have a device temperature that's only, a few hundred Kelvin. And let's see. Oh, what's the price? $120. There's your differential. That's a good measure of how much additional engineering went into this one. Twice the cost, even though it's narrower band. But it does actually have a good amount of gain for a low noise amplifier. So it may actually have successive stages, maybe like inside this device is a front end that only gives maybe 10 dB a gain, and then another stage that gives you another 10 or 15 dB that's not quite as low noise. But it doesn't matter so much at that point. Yes?
This wire is pretty low over there. Is that normal? Like
Yes, the voltage standing wave ratio. What that means, everything is kind of referenced to 50 ohms. So that if you connect this guy, it's got an SMA connection, and you put a 50 ohm cable to feed it, the voltage standing wave ratio, which is really a measure of how much is reflecting. Voltage wave standing wave ratio of 1 means 0 power is reflecting. 1.2 means that there's going to be a little reflected wave, and there's going to be some constructive and destructive interference, such that the ratio of the peak constructive to the lowest destructive null or low point, it's not a null, but it's a low point, that ratio is 1.2. That's what VISWAR means.
higher?
Let's see. That's a good question. This is a good spec to read. So let's check VISWAR. We didn't call it out on the last one. Yeah, this has a higher one, 1.5. So maybe they didn't quite engineer the matching quite as well. 1.5 is not bad. You can live with that in RF. It is actually still well below half the power being reflected. VISWAR as a value tends to exaggerate the reflection. It doesn't take a little reflection makes a much larger VISWAR. However, keeping that in mind, why would you not care? Why would you not invest as much engineering in matching this device? Well, first of all, it's a much broader band device. It's harder to get a VISWAR that's really good over a broadband. So they're giving sort of their nominal typical value, which is across the band likely, maybe the average of all the VISWARs at all the frequencies. And what's more, you don't really care as much. You might lose 20% of your signal power in reflection instead of 10%. But because this is not a low noise amplifier, nobody cares. Nobody cares. Yeah.
Affect the amplifier?
Does the reflected wave affect the amplifier? That's a really good question, too. It does not necessarily reflect the amplifier. In fact, most of that VISWAR spec is actually at the input. So it might affect whatever is feeding this amplifier. Usually at low signal levels like this, it doesn't matter. What it really just means is that you're wasting some of the energy. It's not making it all the way through the device. So that's the only real effect. In some scenarios, you can really do damage to your amplifier at high power levels, for example, if your VISWAR is too high. The first time I ever taught transmission line theory in electromagnetics class here at Georgia Tech, I was at a conference. I was playing hooky from class, and I ran into some Motorola engineers. And those engineers said, "Well, what are you teaching in class, Professor Durgan?" I said, "Oh, some transmission line theory." I said, "Oh, man, I got a transmission line story for you." He's talking about this time he was transmitting power. He had a really big power amplifier, something in the kilowatts probably, hooked up to an antenna with this really beefy cabling out on the roof, coaxial cabling. And he was transmitting, and he had set the thing up, and he was wondering why he wasn't receiving anything. Well, it turns out that they had actually kinked the cable at some point in the installation. So there was almost like a short circuit there, right? It's a VISWAR of infinity at that point. You have peaks and nulls. And he said when he looked out onto the roof, the cable had actually, you could physically see lambda over 2 bulges along the cable, where like the current was at a constructive peak, generating a lot of ohmic heat and resistance, and it was literally cooking the dielectric, causing it to swell and fry inside the cable. And I think he might have actually damaged his amplifier at that point because all of that wattage was going right back into the input. That's a case where VISWAR is extremely important. If you have other amplifiers feeding this, VISWAR is sometimes important because not all amplifiers are stable if you reflect too much power back into their output. So if this amplifier is being fed by another amplifier, and you're reflecting too much power back into that amplifier, then that amplifier could start to self-resonate, and you basically just get saturation. You can't send interesting data. So that's a good question. Good question.